This lesson is going to be about conservation of energy calculations, and the learning target is to be able to use conservation of energy to calculate the potential and kinetic energy of a system, and really to understand how this energy is transferring and transforming throughout this system. So the big idea behind this whole lesson is conservation of energy, the idea that energy cannot be created or destroyed. If we have a system and we draw a boundary on that system, we have something where we have our system and we're drawing our boundary in it, whatever goes in as far as energy has to come out. We have to have the exact same amount of energy. Now that energy can move and cycle and transform within the system, but on the other side of the system, we have to have the exact same amount coming out. And if we have a closed system, right, a closed system would be a system where we're not allowing any energy to come in or energy to come out. If we draw a boundary around that system, making it closed, the amount of energy inside that system has to stay the same. And that's going to lead us to this idea of mechanical energy in a system staying the same. And so how does this apply to kinetic and potential energy? Because that's what we're trying to do here. Well, if you look at this skater, right, let's look at the left side first. Right, he's up on the top of this right side. And remember that we can see what is potential energy over on this graph. And remember that that's based off of his height off of the ground. Now you can tell that he doesn't have a whole lot of kinetic energy here, because when he's at the top and he's almost turning around, he slows down really slowly, gets up at the top, and then turns around. His speed is really low when he's up at the top. So he doesn't have very much kinetic energy, but you can also see what his total energy is. And so if we look over this other side, let's get rid of this. If we look over and we compare these two charts here, and we've got him now at the bottom, and he's not exactly at the bottom, but he's pretty close to the bottom of his turn. You can see that because he's just a little bit over his turn, he does have a little bit of height here, and that's leading to his potential energy. Now you can see that he's moving a lot faster at the bottom of this ramp than he was over here, and so his kinetic energy is much higher. But if you look at his total energy, if you look at this total energy here, they are the exact same. This is the same skater. They haven't changed at all, because all of his potential energy got transformed into kinetic energy as he was going down the ramp. Because his height is decreasing, he lost potential energy, but whatever he lost, he made up for in kinetic energy. And so this is an example of this big idea that energy is not being created or destroyed. It's only being transformed into different types within a system. The total energy is going to stay constant within that system. And as you see, as he goes back up on this left side, you can see that this is a situation where his total energy is the exact same as the other two, but now he's splitting his kinetic and his potential energy. And you can see that he's gained some more height, right? And because he had to transfer some of that energy, his kinetic energy, his movement energy into potential energy as he was going up the ramp, he has a pretty even split here between potential and kinetic, but his total energy remains the exact same. And so as we have a system, as we put energy into a system, somehow he had to get to the top of that ramp. And as he got to the top of that ramp, he's not moving. He has potential energy, no kinetic. And there's also a total amount of mechanical energy in that system. And that amount of energy, that total energy, does not change in his entire path. The whole time that he is moving in that system, mechanical energy stays the same. And so we can actually calculate this. The total mechanical energy equals the potential energy plus the kinetic energy. And that's going to be very useful for us as we go through some problems here, as we try to describe his movement in these situations. So this problem here we have, if a skater has 250 joules of kinetic energy at the very bottom of his path, right where he's at now, how much potential energy will he have at the very top of his path? And we can see here that he doesn't have any potential energy because he's right at ground level. And so his height is 0, so he has no potential energy, but he does have quite a bit of kinetic energy. And remember that as he goes up to the top of this ramp, this kinetic energy is going to be transformed into potential energy. And we remember that the total energy, and I'm going to say mechanical energy here, equals the kinetic energy plus the potential energy. Right, so remember, when he's at the very, very top of his path, right when he gets up to here, his velocity is going to equal 0 because there's that split second right as he turns around when he's not moving. And so at that point, his kinetic energy is going to be 0. Right? So what we can do is we can find out how much total mechanical energy at the bottom, and I'm just going to label this B for bottom. This equals his kinetic energy. So we know he has 250 joules of kinetic energy right at the bottom. That's where he's at right here. And he has 0 potential energy. We know this because he's sitting right at the bottom. And so what we can do is we can find the total mechanical energy of this system is all of our kinetic energy. And so we know that that total mechanical energy, the amount of energy in this system, isn't going to change. And so when we start looking at what is his potential energy going to be at the top, I'm going to label this one T. I know that his energy has to be 250 because it's not going to change this whole time through his path. Well, I know that that has to equal his kinetic energy plus his potential energy. Right now, we already said that when he's at the very top, right, when he's up here, his velocity is 0. And because his velocity is 0, he's not moving. When he's not moving, he doesn't have any kinetic energy. And so that means his kinetic energy is 0 joules. Right, so this we can pretty much ignore here. And we know that his potential energy at the top is going to equal the same as his kinetic energy at the bottom. And so he's going to have 250 joules of potential energy at the top of his path. So we can look at another problem here. If a 75 kilogram skater drops into a half pipe, which is 10 meters off the ground, how much kinetic energy will he have at the bottom of his ramp? So what we're going to start off doing here is we're going to find the mechanical energy. So we're going to say problem 1 here. Mechanical energy equals KE plus potential energy. Now he's at the top. Now I know that this right here says that there's kinetic energy. We're going to completely ignore that. When he's dropping into his half pipe, he has no, not joules, he has no velocity. And so his kinetic energy is 0. Right? So what we have to do is we have to find his potential energy at the top. Now I know his height is 10 meters above the ground. And so I can take my equation for potential energy. There we go. Equals mgh. I know that my mass equals 75 kilograms. I know that my acceleration due to gravity is always 9.8 meters per second squared. And I know that my height is 10 meters. And so I can plug these into my equation, calculating out my potential energy. I have 75 times 9.8 times 10. And that's going to give me a potential energy of 7,350 joules. And so because I now know my potential energy, I'm going to get rid of all of this, all my work here, and I know that that's going to be my mechanical energy at the top. That's going to be the total energy of my system when I'm just starting off on this half pipe because he doesn't have any kinetic energy. Right? So ME equals 7,350 joules. Right? Because that was my potential energy at the top. And so now when he's at the bottom here, we're going to try to figure out how much kinetic energy will he have when he's at the bottom. And now I know that when he's at the very, very bottom here, my potential energy equals 0 because he doesn't have any height. Now there's a little bit of potential energy. We're going to ignore that right here. He's at the very bottom of his path. And so when he's at the bottom, I know that my mechanical energy, my total energy, equals KE plus PE. Well, I know that my mechanical energy is this number right here. So I have 7,350 joules. I also know that, like I said over here, my potential energy is 0. And so I can get rid of this because that is 0 joules. And I know that my kinetic energy is going to equal whatever my potential energy was at the top because all of that energy is going to be conserved. So at the bottom, I will have 7,350 joules of kinetic energy. So now we have a little different problem here. if a 75 kilogram skater has a potential energy of 150 joules and a kinetic energy of 350 joules, what height will he reach at the top of his path? Now, this is a tricky problem here. So we're going to think about all of the equations that we have and what could possibly help us to solve this. So I'm going to start off actually by writing out all of the equations that we have. We have mechanical energy, this is an E, equals kinetic energy plus potential energy. I also know that my kinetic energy equals 1/2 mv squared. I know that my potential energy equals mass times gravity times height. And so when I look at my problem, I'm looking for the height. And so I look for the equation that is going to get me there. And I'm trying to find my potential energy because I see this little h over here. So I think, okay, that's the equation that I at least want to have at the end. So I'm going to set that off to the side here. Potential energy equals mass times gravity times height. Now, I do have a potential energy here. Right? I do have a potential energy in my problem. Its potential energy is 150 joules. The problem with using that potential energy to find my height is that will tell me what height he's at right now, right? Before he moves any higher. Whoops, that's supposed to go all the way down to the bottom. But the problem is that that's not going to tell me the height that he is at the top of his path. And so what I'm going to try to find is the potential energy that he has when he gets up to the top of his path. What I'm going to do on the way there is I'm going to use this mechanical energy problem to find out how much total energy is in this system, right? How much overall energy is this skater holding while he's on this ramp? Then when he gets up to the top of the ramp, I know that all of his energy is going to be potential energy. And so therefore the mechanical energy will be the potential energy that I'm looking for here. And so let's get going on this. So we have our mechanical energy of the system equals my kinetic energy plus potential energy. So I have my ME equals my kinetic energy right here of 350 joules. Now my potential energy, like I said before, is 150 joules, this right here, right? So those added together gives me a total energy in this system of 500 joules. Okay, so now what I know is that when he gets up to this point right here, up to the top of his path, his mechanical energy is still going to equal 500 joules because energy cannot be created or destroyed. So whatever we have when he's at this point here has to be the same amount of energy that he's went up here. It might be a different type, which we know that it's going to be all potential energy, but it has to be the same amount of energy. And so when he gets up to the top of his path, we're going to get rid of some stuff here. Whoops. That's not an eraser. There we go. Okay. So I know that my mechanical energy, and I'm just going to write this, mechanical energy at the top equals my potential energy. That's because at this point, my kinetic energy, when I'm turning around, equals 0 joules. Right? So at the top, I know that my potential energy equals 500 joules. Right? And I know that my potential energy equals mass times gravity times height. Here we go. Now we're going to do some substitutions on here, some moving around of our variables. So we're going to divide both sides by mg. We're trying to get h all by itself. Divide both sides by mg. And what I'm left with here, let's change colors one more time, is h equals 500 joules divided by mass times acceleration due to gravity. Now here we go. We're on the last step. We're finally there. I'm going to try to move everything all at once. Some things moved, some things did not. Now what I'm looking for here. I know that my acceleration due to gravity is always 9.8. Right? My mass is right up in here. We have a 75 kilogram skater. So H equals 500 joules divided by 75 kilograms. 9.8 meters per second squared, that goes up in there. And my height in this problem is not very high at all, 0.68 meters. would be the answer to this problem, would be my height. Wow, that's a big problem. But it's all possible due to the fact that energy is conserved in a system. So whatever we have at any point in there for our total energy, that's what we're going to have at any point in that skater's path. So the big idea in this lesson is that conservation of energy, that energy cannot be created or destroyed. Whatever we have at the start for our total energy has to stay the same all the time. And in this case, it equals kinetic energy plus our potential energy. When we're at the bottom of the ramp, it's all kinetic energy. When we're at the top of the ramp, it's all potential energy. And I hope that this helps you to understand the conservation of energy and how we can make calculations using it.